afternoon, Fancy Meat Computers. How are you all doing on this, the loveliest 24th of Wednesday, November in 2021? How's it going, folks? I've got a one person in the chat who is livening up the chat. I always appreciate that. Not a good afternoon, never a good afternoon. I want to commit all the sad. Well, just make sure that you've got all your branches merged before you commit sad. Three viewers. You know what they say. Get commit, get push, get out. Ha ha. In case of fire, get commit, get push, leave building. So, as a follow-up to that, we were talking about Project 3 yesterday, and I inadvertently noticed that one of your colleagues, who we shall, for the purposes of this discussion, call Agent Q, I noticed I had a submission from Agent Q already, so I decided to get in contact with Agent Q and ask Agent Q how the project went. After, of course, I had reviewed Agent Q's assignment, or the project, and noticed that it is, yes, all the bits and bobs are there. Obviously, I didn't do a deep dive to see if every single line was correct, but all of the pieces that were supposed to be there were there. So it's like, yes, that's an actual submission. So I asked Agent Q how long it took him or her, and Agent Q responded with a few hours, a number of hours, sort of. I got the vague impression that it might have taken Agent Q between 3 and 5 hours. Agent Q did not cite days. Agent Q cited hours. So there you go. That's how long it should take you to do it. Nah, that's not fair. It's not fair to use one student as a measuring stick for another. But I just thought it would be interesting to you, perhaps, that it is possible to get it done not too bad an amount of time, especially considering like one of the sort of quote-unquote questions on Piazza was quite humorous if you haven't seen it yet. This person who has said this, it's like, yep. I think I broke someone. Can I say I broke someone? The hard part is picking where to start. Yeah, I guess. I would say that I tried to help you along with that with the grading scheme. Start with the Booleans. They're the easiest, right? But, yeah. Anyway. Let's see. Are we going to get 12 people today, or are we going to be stuck at 7? Have we stabilized in terms of viewership? I think we've stabilized in terms of viewership. Oh, did it go up? No, it didn't. Okay. All right. So, we should continue along the track that we were currently on. So, proof by logical relations. So, we were talking about how we would go about proving the property that we want to prove. Remember, we're talking about the termination of typed lambda calculus. Termination and normalization are essentially and effectively the same thing in our context. The property of normalization is that you get to a value in finite time. This property is highly related to the halting problem, or the idea of halting, because of course once we reach a value we no longer execute anything in the program. So once you have hit a normal form, the program halts. So essentially, proving normalization is the same thing as proving halting. Now this is interesting because the halting problem, traditionally speaking, is undecidable for Turing-complete languages, of which lambda calculus, untyped lambda calculus, is. However, we went to some lengths to demonstrate that if it's typed, then you can't have a divergent function, right? The thing that makes lambda calculus Turing-complete and the thing that makes lambda calculus Turing-complete and the thing that makes the mechanism by which you can have an infinite calculation in lambda calculus is the existence of divergent functions, of which the omega function is a good example. So, essentially, we went to some length, taking sort of the omega function as an example of a divergent function and demonstrating that the typing doesn't work out for reasons of the definition of equality over infinite sets. You can sort of, in your brain, extend that logic to any of the divergent functions which we studied previously, including the y combinator and the fixed point combinator. So, in essence, so how would we go about proving this, right? The problem, sort of, halting is like a difficult property, right? While we did sort of prove termination in the untyped arithmetic expressions, we haven't really talked about it since, so this will be, this is how we're going to go about it. So, we're setting up a proof by logical relations. So, the idea with this proof is essentially we are performing an induction over the types themselves, right? So with the type system that we currently have, considering only simply typed lambda calculus combined with a base type, combined with an atomic type, we only have two types, right? We've got A, your atomic type, and we've got the type constructor T arrow T, right? So, taking the two of those together, you can see those as being an inductive kind of structure, right? Because it's a recursive structure, it's an inductive structure. So what we're trying to set up, right? We're trying to set up the idea that if the input to a function halts and the function itself halts, then the output will also halt, right? So we define a relation R that, we define a set. It could, you can think of it as a relationship, a relation between terms and the Boolean truth values. You can think of it as a predicate. You can think of it as a set that is a subset proper of the set of terms. Full screen, yes. all of those things are valid ways to think about R in this context. But what R is it is the property of halting. So the subset of the terms which halt and have type A will all be elements of R sub A. The set of terms, the subset of all terms which have type T yields T and halt will be elements of R sub T yields T. Now the trick here is we're trying to prove that all well-typed terms are included in R. That's like, there are a couple of things we have to prove, but that's one of the important ones. So, if we were to define R a bit more formally, so T is in RA if it halts, but things are a little bit more complicated with the case of a function, right? We can assume sort of via either your inversion lemma or the canonical forms lemma, whichever of those you wish to bring in. Anything with type T1 yields T2 is a lambda abstraction where the argument is typed T1, right? The abstracted variable. So, it's not sufficient to just prove that the abstraction itself halts, right? The part that screws it up, the part that causes divergence, is the fact that each application may increase the number of redexes, right? Redex being reducible expression. So, like, for example, like, just for the sake of argument, we have, let's say we have the omega function, right? So we have the omega function that evaluates to itself. Here's a question. What happens to this guy, right? Or maybe we need to maybe that doesn't work, but at any rate, you could see, like, you can see possibilities of, like, the number of redexes not just staying the same, but increasing over time, right? I think I would need more abstractions here, but, anyway, so that doesn't particularly work because I'm not church, but, you can imagine, hypothetically, a possible scenario where you could construct a term in lambda calculus that would never, it would never stop increasing the number of redexes every time a function was applied, right? Maybe you could think of it as like a fixed point combinator that like generates instances of itself, right? And those also have to be solved, so it like replicates itself each time. But anyway, kind of like Fibonacci, but without the stopping condition. Yeah, there's one for you. So if you took the fixed point combinator and you ran it through Fibonacci, or you ran Fibonacci through it, and you removed the stopping condition for the Fibonacci sequence, you would have a term that like doubles the number of redexes it has to calculate each time it tries to process itself. So it's sort of that I would consider to be strongly divergent. But anyway, so the idea is that we need to be concerned about what happens after after function application, right? So we're starting off with the condition that for some term t, which we know is a lambda abstraction, we know that this halts. Well, pardon me. We know that it must halt, and in order for it to be in this set, whenever we have some arbitrary other term s, which is an element of R sub t1, we can conclude that if you apply s to t, that result is in R sub t2. Right? In other words, we are concerned that the property of halting is preserved through function application. That's what we're trying to prove, that halting is preserved through function application, presuming that the input to the function also halts and is well typed. So, yes. So, any questions? I realize that was like a long recap, but it's fairly technical stuff, so hopefully you guys... is everybody up to speed? Is everyone up to speed? If both function and input are well typed, the output will halt. It is new, so baby steps. Yeah, okay, we'll baby steps this. So if both function and input are well typed, the output will halt. Well, that's what we're trying to prove, right? So that's the inductive step, right? The base case is that, you know, it just halts regardless of, you know, if it's not a function application, then it halts, right? The inductive step is, does it also halt through function application? So yeah, we're like, that's the property that we're intending to prove, right? And by the end of it, we will have proved it, but we're going to be using a new technique to do so. So, I guess I'll preface the rest of this lecture by saying the textbook considers this chapter optional, but it also says that this is one of the most elegant proofs in the textbook. I'm not sure if I consider it elegant yet. I think I'd have to, you know, take it out to dinner and, you know, talk to it, you know, really make friends with the technique. Maybe go to the movies with it first. I don't know if I'm ready to... I'm not sure if I'm ready to consider it elegant or not. But yeah. So, anyway. So, essentially... this slide leads from the last... So, in this case, proof by logical relations is a form of induction over types. If we wish to show that some property P holds for all well-typed terms... we start by demonstrating that all terms of the base type possess the property. Otherwise, you've got no base. Otherwise, all your base belong to us. Next, you want to prove that all terms of type A yields A preserve the property P. Then, from there, you would want to prove that all terms of type A yields A yields A yields A also preserve the property of preserving the property P, and so on and so on, and so on and so forth. In this particular case, the property P that we're talking about is halting. But you are opening the door for it, so I think elegance is implied. That's true, I am holding the door open for it, so... So, in essence... So in essence, you know, this is just successive applications of T yields T, with T being substituted for whatever the previous tier was, right? This is an inductive structure. So we can accomplish this result in general by defining a family of predicates indexed by the types. So for the base type A, the predicate is just P itself. For functional types, it says that the function should map A, values satisfying the predicate at the input type, to B, values satisfying the predicate at the output type. So essentially, we're trying to verify that if you start off at a well-typed term, you must end up at a well-typed... Well, sorry. If you start off with a halting term, you will end up with a halting term, right? Our proof of normalization, therefore, has two parts. We first observe that every element of T is normalizable, which is immediate from the definition. We then show that every well-typed term is an element of T. So, essentially, we don't have to worry about the base case in this particular instance because it's immediate from the definition, right? We have defined the set R sub A such that it halts. Not only does it halt, it's a bidirectional thing, right? So if T is in this set, it halts, and if it halts, it's in this set. So there are no elements that are in the set that don't halt, and there are no halting terms that aren't in the set. They are set equal. So that takes care of the base case. In order to demonstrate the second property, we will split the proof into two lemmas. So, number one, we will demonstrate that halting is invariant under evaluation. So, that is to say, if we have some term T which is well typed, and we have an evaluation from T to T prime, then we have T being an element of RT, and T prime is an element of RT, and one implies the other, and like so. Let me rephrase. We have T being well typed. We have an evaluation from T to T prime. We then wish to demonstrate that if you start with T being an element of RT, you can derive T prime being an element of RT, and in reverse. So we want to prove that if T prime is in RT, then the original T must have been, right? This is a very easy proof. The second one isn't going to make much sense. I just put it up there so that you can see it. It's going to require some setup to understand what's going on here, so I'm just going to skip it for now. But this is just to demonstrate we're going to do two theorems, or two lemmas to prove our theorem. So let's talk about the first one. So if I recall in the textbook, they kind of just Peirce kind of just glosses over it and says, you know, well, you can probably figure this one out yourself. So I think I filled this one in myself. Give me just a second to verify that. Nope, never mind. There's a decent description here. I must be thinking about a different lemma. So, let's talk lemmas. Halting is invariant under evaluation. So, proof is by induction on the structure of the type T. First, it should be immediately clear that if T halts, so should T prime, and vice versa, right? That should be obvious to everybody here, right? Like, obviously, if you're on a single evaluation chain and evaluation is determinate, which it is because of call-by-value semantics, because we're not proving it for full beta reduction here, we're proving it for called-by-value semantics, it should be obvious that if two terms are adjacent to each other on an evaluation chain, and that, like, if one is on a halting evaluation chain, so is the other, because they're on the same evaluation chain, right? That should be immediate and obvious. But that's also not what we're trying to prove. The thing that we're trying to prove is somewhat stronger, right? The thing we're trying to prove is that T and T prime must be shown to be members of the same set RT, right? So, let's begin by considering the only if case above, right? So let's imagine that we have RT for just T. We're trying to show RT for T prime. So far, so good? So far, so good. Sorry, what is RT again? Good question. I'm going to sneeze. I think I'm going to sneeze. Am I going to sneeze? Ugh. Yes, I sneezed. So, I'll answer the first question first. So what is RT again? RT, all RT is, right? If you imagine the set of all possible terms, RT is the set of those terms which halt and are typed with type T, right? So we're actually talking like we're talking about a set of different subsets, right? For each type that exists, there is a corresponding set of terms that have that type and halt. That's what RT is. So, question, why is that a strong proposition? Inclusion of the terms in a set. Because it's more restrictive, right? It's a stronger statement to make because it's harder to show that, right? Like you can show that if R1 halts, R2, like, pardon me, if you can show that T halts, you can show that T prime halts easily, right? Because they're on the same evaluation chain, that argument that I just made. What we're trying to say here is not only do they halt, if one halts, the other halts, they're in the same set R, right? So, question, since we know typing is preserved, isn't this also immediately obvious? Yeah, you know, not too bad. You know, yeah. I don't know if they use the fact that typing is preserved here, to be honest with you. But, well, at any rate, it might be a recapitulation of the preservation of typing, actually, but we'll see. So, if T is our base type A, there is nothing more to show, right? That's fine. Again, the only tricky case is where we have a functional type. Ugh. Pardon me for pardon me for just a moment, folks. Sorry. Give me one sec. So if T is equal to T1 yields T2, we need to work a little bit harder. So let's assume the following. Let's assume that T is in type RT. Let's assume that S is in the set RT1 for some arbitrary S. So we don't care what S it is. We're not going to pick a particular one. By definition, we also have R of R sub T2 of the application of S to T. So we also have T of S yields T prime S, right? Or S applied to T is evaluated to S applied to T prime because of the evaluation rules, right? So if you remember, we already have T evaluates to T prime. That's a precondition of the congruence rule for function application. So we have to evaluate T prime first, which is convenient because that also means we don't need to know what S is. The induction hypothesis for type T2 gives us RT to T prime S, right? So the induction hypothesis here is the thing that we're trying to prove, but on as applied to the subterm. Since the selection of S was arbitrary, this holds for any possible S. Therefore, the definition of RT also gives us RT prime. Bing, bang, boom. The argument for the other direction is analogous. Cool. Make sense? Maybe that makes sense? So, just to remind ourselves, our ultimate goal is to demonstrate that every term of type T belongs to RT. The next part of the proof proceeds by induction on typing derivations. Of these, only the case of lambda abstractions are interesting. Mark says, everything you're saying makes sense on its own, but putting it together is analogous to bashing my head on the wall. So, sorry. So, understand that, like, this is not the type... I would never expect you to produce this type of proof, right? Like, this proof was a scientific paper in, I think, sometime in the 70s, I believe, but I can look it up. Let's see here. Standard proof method was invented by Tate, 1967. So this was a scientific paper that was published in 1967 that made it into the textbook, right? So you are not expected to reproduce the amount of work that is necessary to write a scientific paper on the exam. It's just not Hoyle, you know? But, you know, still, it's, you know, to some degree we're taking it on the authority of math that this works, right? So, you know, like if you can't get the logic to click, please continue to think of the proof as being true. Which I know is a cop-out, because, like, in this class, we're supposed to prove everything from the ground floor, but, you know. Anyway, so, the next part of our proof proceeds by induction on typing derivations. Of these, only the case of lambda abstractions are interesting. Since we are arguing by induction, showing that a term, lambda x with type T1, T2 belongs to R T1 yields T2, we'll need the induction hypothesis. Specifically, we need to show that T2 belongs to RT2, right? How we immediately run into a problem, however. So, here's the problem, right? We're trying to say that some lambda abstraction is inside of R T1 yields T2. In order to show that this expression has type T1 yields T2, what do we need? Right? Think back to the typing rule. What do we need? We need to know that the type of T2 is type T2. But herein lies the problem. It's a subterm, and essentially we don't have gamma here to support us. So, although the lambda expression binds x to T2, if we consider just T2 by itself as a subterm, any occurrences of x inside of T2 will be free. So it's like, if you have a lambda abstraction, and you have T2 inside of it, and you peel off the lambda, and just look at T2 on its own in isolation, that thing doesn't type check. It requires the context of the surrounding lambda abstraction in order to bind the variable so that it is typed, so that it can be typed by the type checker. We have defined RT as the set of closed terms of type T, right? So that's another condition that we baked into our relation here, or our logical relation. So we immediately have a contradiction, right? Like, how are we to rely on an inductive method that relies on typing T2 as a subterm when we can't type T2 as a subterm without passing that information through? We will use trickery and deceit. So, the problem on the previous slide is resolved by using a quote-unquote standard trick, which generalizes the induction hypothesis. Instead of requiring T2 to be closed when it isn't, we can prove the lemma for all closed instances of an open term. So this is trickery, right? A lambda abstraction can't type check if it contains free variables. We therefore know that T2 is one substitution away from being a closed term. If we prove that T2 is in RT, then once all free variables have been substituted with closed terms, that's good enough. So you may be asking yourself, we went to all this trouble to set up gamma. Why can't we use gamma in this case, right? So it's a question of set membership, right? We're not interested so much in the evaluation mechanisms here, or even the typing mechanisms. We're trying to determine the set membership. We're trying to see which RT T2 will fall into, right? In order for the induction hypothesis to work, right, we need T2 to be well typed, right? But anyway, so hopefully, so we can't use gamma because, it has to be a closed term, right? So another way of saying closed term is to say that you're typing it with a null gamma, right? And we use that phraseology like on this slide, for instance. This is like typing with null gamma. So because of the way that we've defined RT must be closed terms only, right? So what it means to be a closed term is to be typable with a null gamma, right? Because what gamma does is it types all of the terms, all of the variables that are free inside of the term. So if you are relying on gamma to type free variables, then you have free variables, then you're not a closed form, then you're not in RT. Make sense? If I had thought of that at the time I was making these slides, I would have put a slide in about that. Where are we? Trickery and deceit. Yes. So, if we prove that T2 is in RT, once all free variables have been substituted with closed values, that's good enough. Is that open term T2? I.e., we can't guarantee no arbitrary substitutions on T2. Yeah, essentially. That's essentially the point, is that we can't guarantee that there are no arbitrary substitutions in T2, right? So, rather than have arbitrary substitutions, what we're going to do in the theorem itself, and we can now intelligently talk about the theorem, is we're going to simulate all of the possible substitutions that could occur on the term, and we're going to require certain properties from these substitutions, right? So we now introduce this idea. So now we're introducing the gamma, right? But we started off with a blank gamma. So this is like, if we take all of the free variables that might be in T2, or in T in this case, and we throw them into gamma as a precondition, that's where we're headed with this. So essentially we're going to say take T1, and we're only considering the case where we have all of the possible variables that might be free in it, and we apply substitutions to those variables. It just so happens that this, lines up with how things actually work inside of the lambda abstraction itself. So, if we have x1 with type T1, x2 with type T2, all the way to xn with type Tn, if all of that proves that T has type T, and v1 through vn are closed values with types T1 through Tn, and for all I, which are elements of T1 to n, these values are also in R, RTI, right? So each one of these T's has attached to it a separate RT, right? So each value that has each type also halts, right? Then RT, we're trying to prove that that if you take T and you perform all of these substitutions, so x1 subs for v1, x2 subs for v2, xn subs for vn, then that is inside of our halting set. Haha! That is to say, let's assume we have a set of variables x1 to n having types t1 to n, which prove the term t as having type t. Because t can't be well typed if it contains free variables, and gamma indicates the types of bound variables, x1 to n is the set of, quote, free variables in t. Next, we hypothesize a set of closed values matching the types of x1 to n. We show that substituting each xi for each v in t yields a term that is in RT. Good. We will perform case analysis over typing derivations. So, our first case is t-var. So if we have t-var, we know that the term is one of the x's in here, right? And that the type is the type corresponding to that x, right? So if it's a variable, it must be free, right? Because, if it weren't a free variable, there would be some lambda binding it, but we know that the top level must be a variable because of the typing relation, right? So it's one of the variables in our list. For t-var to be applicable, t would need to be a variable. It therefore needs to be one of the variables in x1 to n. We'll call it xi. By the same logic, the type of t must be ti. We therefore know that after substitution, t becomes vi. We have already defined all of v1 through n as being in RTI, and t is equal to ti. Therefore, RT. Case closed. Make sense? Three votes, yes. Excellent. So, we will now proceed to the most complicated and interesting case, T-abs. So, if the typing relation here, if that is T-abs, then we know, A, that the term T must be a lambda abstraction. We'll call the inner term S2 and the type S1, so as not confused with the x's which are in gamma, right? We know that if we take the existing gamma, add to that x having type S1, that S2 must be of type S2. And we know that the type T, which is the type of this expression, must be S1 yields S2. So, we have two things to show. Number one, we need to show that t evaluates to a value post substitution. Number two, if we apply some term s, which has type S1, that is in RS1 to t, post substitution, the result will be in RS2. This is to satisfy the condition whereby we will consider this this term to be in R sub t, where t here is S1 yields S2. So, the first of these is immediate. T is a value already, and this property is obviously preserved under substitution. Right? So, think about it this way, right? According to our congruence rules, both t and s must be fully evaluated before the substitution can take place, right? So, it would therefore, be logical that you would get a value back again as well, right? So, anyway, so in addition to the equations on the previous slide, we now additionally have, with no typing context, S has type S1. We don't know or care what typing rule was used to determine that. So, by the fact that members of RT halt, we know there exists some V such that S eventually evaluates to it. By the preservation under evaluation lemma, we know that this V is in R sub S1. Remember preservation under evaluation that we just did? Turns out we needed it almost immediately. By the induction hypothesis, we also have S2 must be in RS2 after substitution, right? It's after the usual, the previous substitution chain with the added substitution of x subbed for v, right? So in this application, right, we know that the input's got to be type S1. We know that it's called x. We have the s that we're applying that is also type S1, so it's a valid substitution, and we are going to replace x for v in S2, right? That in addition to all the rest of the substitutions. So, But this result is actually also the result of just evaluating TS, right? So if we evaluate this guy, right, down to the level of where S gets like S eventually evaluates to V, right? So we'll just perform all of those evaluations, no matter how many there are. And you'll notice that lambda x with V applied yields the x being subbed with V in S2 in addition to all the rest of the substitutions. My. We know, therefore, that RS2 has this, we know that the results of this evaluation, the result of evaluating TS, is, in fact, that's in RS2. So there you go. The preservation of halting under evaluation is bidirectional. So, that is, if we start with T1 evaluating to T1 prime, and RT of T, we can conclude RT of T prime. And, crucially, given T evaluates to T prime and RT prime, we can conclude RT. We can therefore conclude that the lambda abstraction itself before the application was already in R sub 2. Or R sub S2, pardon me. Since S was arbitrarily chosen, the definition of R S1 to S2 gives us the fact that this lambda substitution, or this lambda abstraction with all of the substitutions must be in R S1 S2. Case closed. And I only took 2 more minutes extra to explain that. Any questions? That's the end of class. Questions? Need to mull it over again. Yeah. It's a different style, right? No trouble. Oh. You see the elegance. Oh, there you go. And we haven't even done the last case yet. We'll do the last case on Friday. Oh no, I wanted to save the confetti. Alright. Let's see how our viewership did. Wow, we lost like 2. We peaked at 10, and by say 112, we'd lost 25% of the class, and yeah, this is kind of depressing. You realize it's like an attendance of 6 people means only 5% of you are showing up for lecture. Like, even with it being recorded, that's like an all-time low. And, you know, I'm not obviously criticizing you guys, because you guys are the ones who actually come, but, you know, for all of you people who are listening to this post-fact, get your butt to class. Stop being lazy. And stop not watching the videos. Because there's lots of people that are just not watching the videos. Although, if you are watching the video, again, that's kind of like the same argument again. You're not the problem if you're the person who heard me say, stop not watching the videos. But anyway. Anyway, take her easy, folks. And, yeah. Good luck with the project.